Hi everyone, I'm in the physics lab, and if I take a look outside, the laser light is on, which means the laser itself is on. So let's take a look. Here's my setup. You can sort of see at the beginning, I have my laser here. It produces wavelength of 532 nanometers, bright green light, and the beam goes away from the camera. And what you can see maybe is that the light hits a mirror here. Here's the beam, kind of bright if you look at it. And that mirror redirects the light vertically upward. And then there's another mirror here, which is a little harder to see, and that redirects the beam in this direction. And there are some optical components in the way. The first thing is an attenuator, which makes the beam dimmer. It acts like a pair of sunglasses. On one side, the beam is very, very bright. On the other side, the beam is a little less bright. Then there's a microscope objective. The microscope objective focuses the light to a very, very tiny point, and then the beam gets wider as it moves beyond the focus. This lens, let me show you that way, this lens collimates that light, collects it all, and turns it into kind of a steady beam that's not really spreading out much. This thing here is a beam splitter. It acts like a half mirror. It sends some of the light this way to some other optical components that I'm not using, and it sends the rest of the light along its way. Here is an aperture. It's just a hole to let me control the size of the beam. On the other side, I have a beam that's sort of a nice circle shape, and if you notice as it moves along the beam path, it doesn't really change its size too much. This thing here, this is a set of apertures. It's a screen with a couple of pieces carved out of it. And if you look at it, I can show it this way, maybe against the wall. It has 4 sets of double slits. 4 sets of double slits. And you can see the widest ones closest to my hand, and the narrowest ones are farthest away. Each one of those 4 lines is a pair of double slits. And so when I put that into the beam path, I could look at what the light pattern looks like very far down the road. And what I should see is some diffraction pattern due to that double slit. Let's go back. Here's my laser setup to orient you. I know that it's hard to see everything in the dark. The laser setup is over here. The laser is in this area. The beam is coming across the camera. Here's the double slit. That's the light hitting the double slit. There's the pattern on the screen. And what you can see is a set of vertical, bright, and dark fringes on the pattern. And they're pretty finely spaced. And that spacing depends on the wavelength. It depends on the distance between the double slit and the screen. And it also depends on the separation distance between the slits themselves. And so what we're going to do in class, in our wave physics class, is understand what the difference is and how this pattern is affected by the wavelength, the slit spacing, and the distance to the screen and the laser. So it's a quick calculation. The basic idea for all waves is that the finer the pattern on the aperture, the smaller the pattern, like the closer the slit spacing, the more broad the interference pattern is. So this pair of very broad interference, bright stripes, that's due to the narrowest double slit pattern. And that's true in general for waves.